Hello everyone. So today I'll be talking about oblivious multi-party machine learning on trusted processors. And this is a joint work with Aastha, who was an intern with us, Manuel, Cédric, Sebastian, Felix, and Kapil, my Microsoft colleagues, and Aastha and Cédric are here in the audience. Okay, so let us consider the scenarios where machine learning, multi-party machine learning is needed. So recently our world has been augmented with these cute creatures, where the goal is to catch it with your phone. So how do you find them? So there are there used to be third-party maps, which will basically tell you where the rare ones are. But this all closed down last Monday, so now the way you have to go is just manually go around and look for them. However, all is not lost. In particular, actually all the data is there, it's just split up between the participants. So each user has his own map or her map where they see which Pokemon they have found. So if only there was a way to combine all this data and create a collaborative map that can benefit everyone. So how would the users do that? Well, they can't use something called the Care Bear solution, which is with the motto sharing is caring, because they have very sensitive data, which is the location and the time where they have been. So we need some other solutions. Of course, multi-party machine learning comes up with a bit more serious scenarios. For example, hospitals have different patients' data, and if they were to train the model on their joint data, it would be more useful than if they were to train it on their separate data sets. Again, the question of sensitive data comes in, and they can't just share it with each other. When I say multi-party machine learning, I don't only mean combine the data sets in order to train. I also mean that it can be a prediction phase. For example, there's a decision tree, which is pretty much the one from the previous talk, just a bit more round. And so one would simply take the patient's record and then traverse the tree. And basically, neither of the parties should be seeing each other's data except to get the result. For example, here it's a prediction of the likelihood of a heart disease. Again, probably the hospital wouldn't want to show the model, and not all of the patient's data should be required to traverse the tree. So in this talk, we propose a solution for secure multi-party machine learning. We explore the design space. In particular, we are very different from the previous approaches because we rely on the trusted processors. And furthermore, we harden the code that is actually running on those trusted processors. It protects against very strong attackers, as you will see. And furthermore, we ran it on the real Intel SGX, and as you will see, it gives quite a low overhead. So of course, multi-party computation is not new, and it has existed in cryptography for 20 plus years, where one would encode the data and the code in some particular way, so they can upload it to the untrusted third party, which can basically operate on this data without having to decrypt it. Although there has been an enormous progress in the past few years, it's efficient for some computations, but not general purpose. So what our users are left to do is basically upload their data to the cloud, but also have to supply the keys to decrypt this data. And the second their application has to decrypt this data, basically they declare, my trusting computing base consists of everything that is running on the cloud, which includes the operating system, the hypervisor, and all the other tenants. Quite a big trusting computing base. Instead, we propose to isolate the computation that has to deal with your secrets and secret data. How do we achieve this isolation? Using trusted processors. Do those trusted processors exist? Yes, since last October, Intel started producing them on the laptops called SGX, Intel SGX. And this is what we will use in our experiments. So who are we protecting against? So our trusting computing base consists of the machine learning code that we upload, and as well the trusting hardware. Everything else in the cloud fabric is malicious. So it could be the parties that are participating in the protocol. So the machine learning code is known to everybody. It could be other tenants snooping on our cache, what we are doing. It could be compromised kernel. It could be also a passive adversary who's just seeing how we are interacting with the system. We assume that the machine learning code is not going to do anything stupid, like write out secrets in the plain text. And we are also in the classical multi-party computation model, where the users agree to share the output and whatever will be inferred from the input. But if we wanted to protect against those, there will be like an add-on that you will change your machine learning code and add, I don't know, your favorite differential private mechanism on top of it. We do consider memory and network side channels, but we do not consider time and power channels. Okay, so how we compare with the kind of previous work? Well, we are making a very different assumption as opposed to the cryptographic solutions. We rely on trusted hardware, and in return, we have a very small overhead. This overhead, however, is higher than what is a little bit higher than what you would get with your trusted computing base consisting of the whole cloud, but in return, you get a very small trusted computer base that we have. Okay, so how would the users or the parties use our framework? So they first agree on the machine learning code that they're going to run, and then one of them uploads this code. Then, because the code may have changed or one of the particles have modified, they establish a secure channel with the cloud and verify that it is the code that they indeed put on the cloud, and it is indeed the correct Intel SGX that is out there. And then once that is established, they send the data and the keys. So it's important to note that the access to the data and the keys is isolated from the rest of the system and is only available to the machine learning code. Finally, when the output is ready, it can be sent encrypted to the users with the shared key, or it can stay in the cloud and be queried later on by them. So in our framework, we are protecting the data using encryption. Everything that is outside of this isolated region will always be encrypted. And we protect the code using these trusted processors. But we also protect the accesses that the code is making to the data, so these memory side channels. So what are these isolated regions? So they are called secure enclaves. So it's basically an isolated region of memory which is created by a processor. And the processor will make sure that no one outside can access your memory. So we get the integrity of the code. We also can run remote attestation and check that it is that our code, the one that we wanted, is indeed been put into the enclave. So this enclave is secure. It is living in a very hostile environment, where basically whenever it's trying to get resources like memory, it can be observed as it could be observed, for example, if someone shares the cache. So here we will assume a very strong attacker that can observe everything very precisely at a cache line granularity. And so we will call this a trace, basically each of your accesses. So we protect against such observations, not in an ad hoc manner, but with the following guarantee. If the adversary picks two inputs, and it also sees the trace that was produced, he cannot tell which of the inputs produced it. So in other words, the trace basically only depends on the public data. For example, the size of the training data set or the number of classes in your machine learning model. So we call these algorithms that have this property data-oblivious, because basically the rest of the system is oblivious to what you're trying to do. When trying to achieve this side channel protection, we will assume that the registers are private memory. This is kind of the smallest assumption, smallest private memory that one can probably have. And we'll assume that the manipulations inside of it and the content of the registers is hidden from the adversary. So we considered 5 machine learning algorithms, kind of trying to also cover supervised, unsupervised learning. Some of them do prediction. Some of them also do training phase. And our side channel protection basically consists of 3 kind of parts. So first, we have a library of data-oblivious primitives, and these primitives are used in each of the algorithms. Then we noticed that in some supervised machine learning, like support vector machines or neural networks, there is a sampling phase. And if not done properly, it can be it can leak something. So we propose an oblivious technique for sampling. And then just by combining oblivious small primitives, you don't get an oblivious algorithm. So we have to work a bit harder. And so we do some changes in the algorithm. And basically the width of the lines represents how much effort we put basically in changing each of the algorithms. So today I will be talking about our library, about our sampling technique, and about the two algorithms. But for the rest, please see the paper. So our library of oblivious primitives. So it consists of such things as, for example, greater operator, move, less, and equal. Each of them operates only on registers. This is to avoid the compiler to make optimizations and creating a side channel. So for example, in oblivious greater, we are comparing x to y. We load x and y to the registers, and then we compare them there so that the result actually goes into the register. As you remember, registers are private memory. Yep. So we also have this oblivious get primitive, which basically gets an ith element out of an array, but with the following properties that we want to hide which of the indices that we've accessed. So for those of you who know what oblivious RAM is, it's basically, one would ask why not use oblivious RAM, because its whole purpose is to do exactly that. So why didn't we use it? The first reason is most oblivious RAM constructions assume quite a large Poirot memory. So something like logarithmic in the memory size. And we had only basically constant number of registers. And two, oblivious RAM breaks even only after your data set is quite large, and we didn't encounter that big of a data set. So scanning worked, and our scanning is actually quite optimized. So now I will tell you how exactly we optimize this oblivious get primitive. So here we have the cache, which is, each line is 64 bytes. And as we said, we assume that the observer sees only which cache line we are accessing. And then we have our registers, which is the private memory, which is each register is just 4 bytes. So we know that we can read an address by, we can load the address into the register, but from the adversary's point of view, he will only see the cache line. So he doesn't see which 4 bytes out of 64 that we are accessing. So we build on that and use instead vector registers, which are basically 8 components of 4-byte registers. But the great thing about them is that you can actually load the content of the vectors with a single, in an atomic operation. And this operation is called vp-gather-dt. So basically now, we can access 4 bytes out of 512 bytes obliviously. So we do it in basically constant number of operations, and we do it in 2 steps. First, the adversary, as we said, registers our private memory. So the adversary doesn't see which of the 8 registers that I'm accessing. And second, he doesn't see for each of those registers which of the 4 bytes I've accessed in the cache lines that I've touched. Okay, so this was the primitives. Now let us take a step back and look at the actual training phase of some of the machine learning algorithms, in particular the supervised ones. So in supervised learning, you are given training data, which consists of your features, and then your label y, and then you're training the model. And the way the model is often trained is by taking a small subset of the data and updating your model. And then take another subset, update your model, and keep going. So as you can see, we are sampling with replacement here. So there are 2 problems with this approach. First one, it's not secure if somebody, because the observer can see how many times we touched which records and which records did not participate in updating the model at all. And second, because we are dealing with an encrypted data set, we will have batches of encrypted records. And it's very not efficient to basically decrypt the whole batch and only access one element. So random access is not very efficient. So to this end, we propose to shuffle the records in an oblivious fashion, so that one basically loses the correlation between the pre-shuffled and after the shuffle records. And then the way we now update the model is by simply scanning. We take the first batch, update it, then take the next batch and update, and so on. But you may say, okay, we changed our distribution, because now I can never take the blue records again, for example. So we are sampling without replacement, and we used to sample with replacement. However, we make the following observation, is that from the correctness point of view of the algorithm, actually the only thing that matters is that the distribution produces an unbiased estimate of the expected value, and those two produce that. And also, it's actually more efficient because basically, if each of the colors represent an encrypted batch, we can now decrypt the whole batch and operate on each record and put it back. So in a way, the cost of the decryption is amortized over all the records that we've used to update the model. Okay, so now I will tell you a little bit of the algorithmic changes that we made to the decision trees and matrix factorization. So the decision trees usually would be stored in an array, where basically from the root there is a pointer to the children and so on. There are two things that we want to hide. One is how we actually evaluated the comparison at each node. So for that, we can use our oblivious primitive. And then the more complicated part is that we need now to hide which of the node we actually go and traverse. So here, we don't care about hiding which level of the tree we are, because the height of the tree we declared as a public. But we do need to hide which of the node of the tree we need to hide which node at the level we've accessed. And this is exactly where we are going to use our oblivious scanning technique, the one that used vector registers. So as you could see, there is a random access that is happening, and that is dependent on the condition evaluation. So similarly, in matrix factorization, there are also random accesses happening, but they're a bit different. In particular, in the matrix factorization version that we used using gradient descent, there are two data structures, U and V. And the way basically you're trying to minimize your objective, so you're iteratively updating U and V all the time. And in order to update one or another, you have to make accesses in the other data structure. However, these accesses depend on secret information. We can't use the scanning technique here because U and V are actually quite large. So we had to do something different here. And so what we proposed is to basically interleave these two data structures in some very special way, such that all the information that you need in order to update your row in U is either above or below the record that needs to be updated. So now this way, we can do an update of both U and V by just performing a linear scan. And we do it only once at the preprocessing phase, and then there is multiple iterations. So it's okay to basically place your data the way in order for then later to make deterministic accesses to it. We built our system. We used the Intel Skylake processors, which do have SGX on them. So enclave memory for now is 94 megabytes, but that's probably going to increase. And as datasets, we used some popular datasets from the UCI machine learning repository. We binary encoded them in order to avoid the side channels that would be created by parsing CSV files. And then the way we encrypted data is in batches, because some of these datasets that we considered were, of course, larger than the enclave memory. So we couldn't just load all the memory, all the data, decrypt it, and then access it the way we wanted. So we split the data into batches, encrypted them, and we processed them by reading a batch, decrypting, operating on it, and so on. Okay, so here are the comparison with the baseline. The baseline here is no encryption, no SGX, basically how you would run it. And then the blue comparison is when you use SGX and the encryption. So as you can see, the overhead is actually quite small. So for neural networks and SVM, it is only 1% and 7%, respectively. But K-means is an outlier. And why is that? Well, because K-means does so little of computation that actually it can't amortize the cost of the decryption that you've done. While such, for example, expensive computation like neural network completely amortizes the cost of the encryption that you are doing. So then we added also our data-oblivious protection. And as you can see, it really differs depending on how your algorithm behaves. It can be 3 or 8% for neural networks and SVM. And then for decision trees, for example, it really depends on how shallow or how deep your tree is. For example, some data sets we have 60x overhead or 8x overhead. So it really depends. Okay, so we've been really trying hard on making these things data oblivious. So are we? So we have pen and paper proofs for each of the algorithms where we basically show that the trace that they produce, the input-output trace that they produce, can be completely reproduced by just knowing the public information about your data sets, such as input and output size. Of course, when coding that, we could have made errors. So to validate this, we collected traces at a cache line granularity using Intel pin tool. And so now what you are going to see is two videos of basically the code traces of traversing a tree before we apply our oblivious technique and afterwards. Okay, so here what we have is basically two sets of inputs, input A and input B. And on the x-axis, we have time, and y-axis is their addresses. And basically, the blue points are whenever we access, whenever we make an access. So they're quite interesting, I guess. So they keep going. Okay, so when looking at them, I guess we can make several observations. So first, for example, we can think of what do those things look like. So we can start calling them things. So for example, if something below called Ursa minors, ours can be called Cervus minor, because obviously it's more of a deer than below is of a bear. But kind of more the point is that the deers are running at a different pace on two different sequences. So that is definitely not data oblivious, and it's a clear indication that the traces are very different. Okay, so now then this is a trace, basically same input A, input B, but now collecting traces from our oblivious execution of the code. So of course you're not going to believe me that they're the same, but they are. Also, they are very boring, as sometimes the case with security, but they are data oblivious. Okay, we didn't just look at them and verified. We did write a program to do that. Okay, so in conclusion, we explored the design space for multi-party machine learning. In particular, we proposed this new trust model, or considered a new trust model using trusted processors. As you could see, the performance when you use just SGX and AES encryption is very small. It's 20% average overhead, which is significantly faster than the cryptographic solutions. And finally, if you want to harden the code even further, we proposed memory protection against memory side channels. And I'm 4 minutes faster. I have amazing matrix factorization slides if you'd like to learn more. But I think I'll finish here. Yeah, thank you.
And we have plenty of time for questions, so please line up at the microphone. Seriously. All right, while you do that, since all of you certainly have one question prepared, let me ask you one question. So you mentioned that the SGX enclave memory is currently limited to 94 megabytes. Did you run into that limit at all with the models that you were looking into, and how would you suggest to go beyond that?
Sorry, so all the data sets that we considered, they were larger than that. So we basically split them in batches, so we processed them in batches. But most of the models did fit into that size, so we didn't consider, we didn't run into it, but of course, once I guess you would have to split the model somehow and encrypt them and store it outside and then have to load it, we had some problem with k-means, but we avoided it. We basically changed the loops in a way that it doesn't have to do that. Yeah.
Thank you.
Do you have a sense for how much faster you are than just a generic ORAM construction?
Sorry, could you repeat that?
Do you have a sense for how much better this works than just using a generic oblivious RAM construction? Like, would that be orders of magnitude slower, or?
One thing is that it's hard to compare is that oblivious RAM requires large private memory, right? So the only way we could have simulated oblivious RAM is by having this private memory, right? And one way of simulating it, we'll have to scan it all and over again in order to simulate it. So in a way, we wouldn't be able to. But yeah, I would guess it is a couple of orders of magnitude. But again, it's not very fair, right? Because we knew what we are dealing with. And for some of the things, it would be very bad for matrix factorization. For example, that I can tell you for sure it's going to be orders of magnitude, just because oblivious RAM is not smart enough to figure out that you can do many optimizations there. Thank you.
Yeah, I guess I have a similar question. You also couldn't tell where the break-off point would be, like how large would the memory need to be so that oblivious RAM would be worthwhile using?
Yeah, so I'm going to quote the papers that appeared in USENIX last year called Raccoon. So I think one of their last figures is basically estimating how many times you have to access memory and for watch sizes of n. And I think it was around 100,000 elements, but you have to double check. Yeah, it was something around that.
Hey Olga.
Hi.
So yeah, you're saying that you don't use RAM like because it has logarithmic client memory, but we can use this trick where you can outsource the client memory and access it while keeping the constant client storage. So you can just do like multiple rounds while keeping a constant client storage that will be in your enclave. Have you thought about doing this and using, for example, any ORAM scheme, for example, for your area access?
We thought about it, but again, okay, because I worked on oblivious RAM, so I kind of expected, I had intuition that it is going to be high. It would be nice to see it, but I doubt it's going to be much better than what we are doing, or even better. It's an interesting question. But the trees that we had, they were quite small. I think the largest, the levels were high, but I think we didn't have more than, 60,000 nodes at every point of time. And as you saw, we use all these techniques for optimization, so it's quite highly optimized. And my main reference is the Raccoon paper, which also suggested the same finding. But it is work in progress to come up with the oblivious RAM that would work this way.
All right, any more questions? Then let's thank the speaker.